This is a system of linear equations in 3 dimensions. It's analogous to the 2-dimensional system that we looked at in a previous video, in which we have 2 parallel lines. In that system, each equation of 2 variables is represented by a straight line. In this 3-dimensional system, each equation of 3 variables is represented not by a straight line, but by a flat plane. This system also has no unique solution. How do we go from this system of equations to a solution, or in this case, showing that there is no solution? We start with the coefficient matrix, and that's easy enough. And last time we did a series of row operations, and we ended up with a easy to solve matrix. But when we did that, we did it kind of willy-nilly. So we're going to develop an algorithm for converting a messy matrix into a beautiful matrix. First, we need to define what we mean by a beautiful matrix. And this is what we mean. If there are any rows of zeros, they are all at the bottom of the matrix. Furthermore, reading from left to right, top to bottom, the first non-zero term in each row is a 1. These are what we call the leading ones. Everything to their left is 0. You'll also notice that the leftmost one is also at the top, and it descends in a quasi-diagonal so that the rightmost one is also the bottommost one. Now, these asterisks, they can be anything. They could be 1s, they could be 0s, they could be whatever elements we would have in this matrix, any numbers. But a matrix in this form is so important, we give it a name. It is a row echelon form of matrix. These 1s are key. They are what make it so beautiful, because they allow us to describe all of the variables in terms of one another. Now, if this matrix is beautiful, there is another kind of matrix which is the Holy Grail. Let us add to our already beautiful matrix the additional criterion that the numbers above the 1s, these must also be 0. Anything that isn't either to the left of a leading 1 or above a leading 1 or a leading 1 can be something else. But this is our Holy Grail, because from this we pretty much read the solution, or see that there is no solution, or that there's multiple solutions. This we call the reduced row echelon form. And if this seems like a bunch of gobbledygook, yeah, it's gonna, until we actually put it into practice and see what using this looks like. The Gaussian algorithm will allow us to take any matrix, such as this one, using elementary row operations to row echelon form. Here's how it works. We start by looking at the columns from left to right, and we find the column that has the leftmost number in it. I mean, in this case, they've all got leftmost numbers. So we could pick any of these rows, but the idea is that row has got to go to the top. If this was a 0 here, then we would bring this 1 up. In fact, that's what they do in the book, because we want a 1 there eventually. But since we've got a non-zero entry here, let's use it. So we'll multiply that first row by 1/3 to make that into a leading 1. So 3 times a third is 1. 1 times a third is 1/3. And negative 4/3. And negative 1/3. Now, for the second row, we are going to, I'll write it in, we are going to subtract the correct multiple of the first row so that eventually we want nothing but zeros in this first column. So the multiple is 1. We're just going to subtract the first row from the second row. So 1 minus 1, that's 0. 0 minus a third is negative 1/3. 10 minus 4/3 is going to be 30/3, 34/3. And 5 minus 1/3 is 16/3. This row at the bottom, we want this 4 to become a 0, so we are going to have to subtract 4 times that top row. So 4 times 1 is 4, and so that's 0. 4 times a third is 4/3. 1 minus 4/3 is going to be negative a third. We can just fix that. And then 4 times negative 4/3 is negative 16/3. We want to subtract 6 minus 16/3. So that's going to be 18/3 plus 16/3. Oh, this is painful. And now we've got our 1 with 2 zeros down here. So this is recursive. We have a mini matrix here that we now want to do this all over again with. We'll multiply this whole row by -3 so that we get a 1 up here. And now we want this to be a 0. We'll multiply this row by negative a third and then subtract that from this bottom row. So negative a third minus negative a third, that's going to be 0. We'll multiply this by negative 1/3, which gives us positive 34/3. Subtract that, we get 0. Negative 16 times negative a third is going to be 16/3. 1 minus 16/3. So 3/3 minus 16/3 is negative 13/3. Finally, let's multiply this bottom row by negative 3/13. So we end up with a 1 here. It doesn't really matter what we end up with here. In the book, I think they've got -3 here because this is enough for us to look at this and go, hang on, we have a row of zeros, and then in this part of the matrix, we've got a number. So this implies that 0x plus 0y plus 0z equals 1, which we will not have in any universe of which I am aware. We have shown through the Gaussian algorithm that this system is inconsistent. We have shown algebraically what we could see graphically when those 3 planes failed to meet up in one single point. There is no solution. That is our solution. There is no solution. Let's turn the Gaussian algorithm loose on this matrix. We already have a 1 up here. Yay, we like that. So we're going to keep it. We want all of these to be zeros. So now we need to justify the zeros that I just put here. To do that, I'm going to double this upper row, and I'm just going to put a note here, -4, so we can see what we're doing. -2, 6. And then we're going to subtract 2 minus 2 gives us 0. -4 minus -4 gives us 0. 1 minus -2, that's 1 plus 2, gives us 3. And 0 minus 6 gives us -6. And 5 minus 2 gives us 3. Now to get this 0 here, I just need to subtract the top row from the bottom row. 1 minus 1 is 0. Negative 2 minus negative 2, it's 0. 2 minus minus 1 is 3. Negative 3 minus 3 is negative 6. And 4 minus 1 is 3. Here's an interesting state of affairs. Rows 2 and 3 are identical. So let's turn this 3, we can't turn this 0 into a leading one, but we can turn the 3 into a leading one. So by dividing this row by 3. Now I'll just write in the third row as it is here so we can talk about it. This 3 needs to become a 0 because it's underneath the leading one. We need to subtract 3 times this upper row. Well, we already had 3 times the upper row. It was over here. So 3 minus 3, that gives us 0. Negative 6 minus negative 6, that gives us 0. And 3 minus 3 gives us 0. Okay, so the bottom row is all zeros. And finally, we want this is row echelon form. Let us make it perfect, reduced row echelon form, which in this case means that this needs to become a 0. We need to modify the first row. To do that, we add it to the second row. So 1 plus 0 is 1. Negative 2 plus 0 is negative 2. Negative 1 plus 1 is 0. 3 plus negative 2 is 1. And 1 and 1 is 2. Here is our matrix in reduced row echelon form. Now we'll convert it back to a system of equations. Let's make this row x1, x2, x3, and the final row is x4. Here are our leading variables. x2 and x4 are non-leading variables, so we make up parameters for their solution. So now we have x1 minus 2s plus t equals 2. x3 minus 2t equals 1. That's this row. x1 equals 2 plus 2s minus t. x3 equals 1 plus 2t. That is our solution in terms of parameters. What constraint must we put on A, B, and C so that this system will be consistent? We start with our matrix. We want row echelon form. Our top row is the way that we like it. It's got a leading one already. The second row will add the top row to it because we want that to be a 0. Negative 1 plus 1 is 0. Negative 2 plus 3 is 1. 1 plus 1 is 2. And B plus A is A plus B. We also want a 0 here, so we're going to have to triple this top row and subtract that. So I'll make a note here, 3, 9, 3, and 3a. So 3 minus 3 is 0. 7 minus 9, negative 2. Negative 1 minus 3, negative 4. C minus 3a. We just write that as C minus 3a. We already have a leading one here. Yay! This needs to become a 0 down here. Let's double the second row and add that to the third row. 2 times 1 is 2. Add that to the negative 2, we get our 0. 2 times 2 is 4. Add that to the negative 4. Oh, we get 0. And 2 times a plus b is 2 times a plus b. So let's figure that out. So we've got c minus 3a plus 2a plus 2b. That's what needs to go in here. Let's simplify that. C minus a plus 2b. We can stop here because we have a row of zeros. For this system to be consistent, this must be 0. So we could say C must equal a minus 2b. That is our condition for this system to be consistent. The textbook continues by converting this to a 0 and solving the whole system of equations, and you can try that if you like. In summary, if this entire bottom row is 0 and this is something other than 0, then the system is inconsistent, which means no solutions. However, if this is 0, then the system is consistent. And now the question is, one unique solution or infinite solutions? Let's take a look at the number of variables, which corresponds to the number of columns. We have 1 column, 2 columns, 3 columns. Let's call that number n, and in this case it's 3. Now that we've got a row echelon matrix, we can ask the next question: how many leading ones? We'll call that number R. There's 2, and we'll give it a fancy name. That's the rank of the matrix. Now in this matrix, we've got 3 variables, only 2 of which are leading variables. So that means we're going to have 1 free variable. We need 1 parameter. So the number of parameters is going to be n minus r. So when n is greater than r, that corresponds to infinite solutions. Finally, when we have as many variables as we have leading ones, so leading variables, then that corresponds to a single unique solution. Bob is your uncle.